Alright, so just so you know, we're not going to be going through all of L2 today, but we are going to get a good start on it so we can finish it up on Monday and then practice L1 and L2 on Tuesday and Wednesday. Alright, so we've talked about how the limit of f(x) as x approaches a value does not depend on the value of the function at that point. What that means is that a limit can exist when there is a hole and when there is no hole. A common misconception at this point, since when we start talking about limits, we look at functions that have asymptotes or holes, is that if a function doesn't have an asymptote or a hole, it doesn't have a limit, or that you can only have a limit if there's an asymptote or a hole. And that's just not true. A limit is what happens as x approaches a value, not what happens at that value. So it doesn't matter if it has no asymptote, it doesn't matter if it has a hole, and it also doesn't matter if it's filled in, if it's connected and there is no break in the graph. So in our first example here, we're going to look at 3 different limits. These are pretty straightforward, simple ones. And we're going to use old and new approaches. So we're going to look at, well, let's just start with this one. So we're going to find the limit as x approaches 3 of 4. Okay, so this is my function, 4. If we use an old approach, so I'm going to graph it, this means I'm going to graph a horizontal line through 4. Okay, and then the focal point, or the x value that I'm looking at here is 3. So that is my focal point on the curve. So if we look at what's happening with my y values as x gets closer, so as your function gets squeezed towards the x value of 3, what's happening with my y values? Well, the y's on this side are 4, the y's on this side are 4. So as you get closer, it looks like it would meet at, or it intends to be at, the y value of 4. So we would say the limit as x approaches 3 of 4 is 4 based on the graph. For b, we have a new function. The limit as x approaches 5 of x. What is it? So this is just a pretty simple linear equation. Mx plus b. I don't have a b, so my b is going to be the origin. And then my slope is the 1 over 1. So here's my point here, or my line. And I'm looking at the focal point of 5. 1, 2, 3, 4, 5. So I'm looking at this point here. Okay, so if we look at my function, when I squeeze the function this way, and I get closer and closer and closer to x being 5, if I look at what's happening with my y values, as it gets closer and closer and closer to where x is 5, these values are coming down towards a certain y value. These y values are coming up towards a certain y value. And it looks like that y value, or that height that it intends to be at, is the height of 5. So we'd say, okay, that is 5. Okay, so let's look at one more. The limit as x approaches 2 of this function, 2x squared plus 3x. Okay. Now, I'm going to use my table here as soon as I find my calculator. Okay. So if we put in the function 2x squared plus 3x, and we look at my table, some values really close to 2 are 1.9, 1.99, 1.999, and then 2.001, 2.01, 2.1. So if you notice what's happening with your x's to the left of 2 are getting really, really, really close to, looks like 14, and over here it's going to be 14. And look at what the height's intended to reach at 2, 14. Now we've looked at examples where that would be an error, but this one still has a limit, even though there's not an error, because we don't care what's really happening at that point. It looks like from the left and from the right that you intend to reach that value of 14. So we would say, okay, that's equal to 14. Now we've talked about the fact that with graphing and tables, those are estimations for limits. It's not perfect. And there are algebraic ways to find limits. We're actually going to start discussing them today. Many times you can directly substitute C. So this is your C value, that focal x value that your limit is focusing around. Sometimes you can directly substitute it into a function to find its limit. Because notice here what happens. If I take 2 and I plug 2 in, 2 squared is 4. 4 times 2 is 8. This is 6. 8 plus 6 is 14. So I didn't have to necessarily graph everything or find a table, because in this case, I would get the same answer, the same limit, if I directly substitute. So that is one algebraic method that we can do to find a limit, is just plug the number in, plug C in. These functions are referred to as continuous functions. So you can't do this with every function, because we've seen functions where we plugged in C and you got an error or something. So we know there's got to be other methods for those ones, but in this case we can plug 2 in and it works. It is a continuous function. This means that there are no breaks. So there are no breaks, holes, or asymptotes. Why would it apply only to these functions? Well, you'll notice that all these functions here, you have a line, and this would be a quadratic if we were to graph it. These are in the families of functions called polynomials. All polynomials are continuous. There's no breaks, holes, or asymptotes. Okay, so we're going to just briefly talk about functions that are not continuous. So in Algebra 2, we had lots of different types of these functions. We had exponentials. Exponentials had asymptotes that you followed. Their counterpart, logarithms. We had square root functions that had a break. We had lots of different trig functions, like secant, cosecant, tangent, and cotangent, all have asymptotes and breaks. We had piecewise functions. And rational functions. Rational is a fancy way of saying fraction. So this would be a function that had x in the denominator. Okay, so that kind of gives us a good list. Okay, direct substitution works. So when you're trying to find limits, you'll actually find that the first step that we always try is directly substitute, because a lot of times it works. So it'll always work unless you get indeterminate form, which is 0 divided by 0, or if the denominator equals 0. So our first step to finding limits is we always try to directly substitute first. But if you directly substitute and you get 0 in the denominator, even if you get 0 divided by 0, that does not become 1, because 0 is the absence of value. So there's no way that an absence of value divided by an absence of value can somehow have value. So that's why it's called indeterminate form. You can't determine any value from that because it means nothing. And you can't divide by 0, and here, same thing, can't divide by 0. Alright, let's flip the page. The rest of the standard is going to focus on the different algebraic techniques you can try and use to find a limit without graphing or making a table. Okay? And actually, before we look at example 2, flip a page to your strategies. As we do new strategies, we're going to add them to this list. So first thing I always want you to try to do first is always directly substitute C into the function. If you get 0 divided by 0, or the denominator equals 0, move on to other strategies. And we'll list those here. Okay. All right, so if we look at example 2, the limit of a rational function. So make an a and a b here. All right. We're going to say the limit as x approaches 1 of x squared plus x plus 2 all over x plus 1. Okay. Just so you know, when we begin these examples, I'm always going to try to directly substitute first. And only then, if that doesn't work, am I going to show you another strategy, or we're going to talk about other strategies. So we're going to go ahead and do it just like how I'd want you to start this problem. I'm going to directly substitute 1 in. So 1 is my c value. It's the focal point that I'm looking at for my limit. Okay. So on the top I get 1 plus 1 plus 2, which is 4. And on the bottom I get 2. Now, I didn't get 0 over 0, and I didn't get 0 on the bottom. So I'm good to go, and I have found that my limit is 2. Now, I'm going to be kind of picky that if you do work like this, you make a final limit statement. And I want to say, or I want to see that you have the limit as x approaches 1. Now, if you already have your function labeled here and you're just writing your answer, you don't have to rewrite the whole thing. You can just label it f of x. So I know that, okay, you're identifying this as f of x equals 2. And that would be what I want you to box. Okay? Let's look at another one. The limit as x approaches 3 of 2x minus 3 over x plus 5. Now, again, we're going to try to directly substitute first. These are rational functions. I know I used that phrase already, but they're called rational functions because you have variables in the denominator, here and here. But that still doesn't prevent us from trying direct substitution first. So that's what we're going to do. Okay, and on the top I get 6 minus 3, which is 3. On the bottom I get 8. Again, I don't get 0 over 0. And the denominator doesn't equal 0, so I'm done finding my limit. All right, my limit statement. The limit as x approaches 3 of my function is 3/8. Now, I could do a table or a graph and probably figure out that the limit up here is 2 and the limit here is 3/8. But this is actually much quicker than doing that. So it's nice to have some algebraic methods in order to solve some of these. Alright, make an a and a b here. Now, you will have sometimes functions that have trig equations in them, or trig parts to them, such as this one. The limit as x approaches pi of your function x times cosine x. Okay. The method still remains the same. We're going to try to directly substitute first. And if it doesn't work, then there's other options we can use. But this is definitely the first option I want to try. Cosine of pi. Cosine of pi is right here. I'm going to use, on the unit circle, that point on that quadrant angle, which is -1, 0. And cosine is x over r, or in this case, -1 over 1. So this value here is going to be pi times -1, or negative pi is your answer. And so you could say the limit as x approaches pi of f of x is negative pi. Okay, same type of deal. The limit as x approaches 1 of sine of pi x over 2. Again, we're going to directly substitute first to see if that works. So sine of pi times 1 divided by 2. So technically this is sine of pi halves. Pi halves is this angle here, which is the point 0, 1. And sine is y over r, or in this case 1 over 1 in the unit circle. So the value of this is just going to be 1. And so because it wasn't indeterminate and you're not dividing by 0, you can write your limit statement. The limit as x approaches 1 of sine pi over 2, or you could write f of x there. I kind of changed it on you. Equals 1. All right. So all those problems ended up being able to directly substitute. But no matter if you can or can't, if you can't, you'll be able to see that because you'll get indeterminate form or 0 on the denominator. And then you have other things that you can try. Okay, let's do this one. The limit as x approaches 4 of x squared minus 5x plus 4 over x squared minus 2x minus 8. Okay. Again, I'm going to try to directly substitute first. So 4 squared, and then 4 squared. Okay. All right, now when I figure out the top here, I get 16. Minus 20 is negative 4 plus 4 gives me 0. Okay, I'm okay so far because I can get 0 in the numerator. But if I figure out the bottom, I get positive 16 minus 8, which again I get 0. Because this is indeterminate form, I cannot directly substitute. So, cross out that work, and then I have to do this another way. We started to talk about this a couple days ago, but when you have a rational function like this, if you can factor, so if we can factor the top and we can factor at the bottom and something cancels, a lot of times then you can directly substitute because you remove the problem and then it works out. So we're going to factor the top here. When I factor the top, I would need x and x, because those two would have to multiply to get x squared. And then the two numbers that multiply to get 4 and add to get negative 5 are negative 4 and negative 1. On the bottom, x and x, the two numbers that multiply to get negative 8 and add to get negative 2 are negative 4 and positive 2. You have a like factor here of x minus 4, so that I can remove. Now once you are able to factor and cancel something, then try plugging c back in. So now we're going to try directly substituting again. And it looks like this time it works. Okay? So if you try directly substituting off the bat and you get indeterminate form, and it's a function that looks like this, so a rational function, we can try factoring and dividing out one of the factors and then try directly substituting again to see if it works. So in this case, you are able to find a limit as x approaches 4 of your function, and that limit is 1/2. Now, this is what's going on with the graph here. With the factor that you can cancel, you have a hole in your graph at x equals 4. Okay, because there's still something going on because it was there originally and made my function 0 on the bottom. So there is something happening there. But because you can cancel, it takes away the 4's ability to be an asymptote and it makes it just a hole in the graph. However, this value of x equals negative 2, because that doesn't cancel, you have an asymptote at that x value that would make the bottom 0 now. But because negative 2 isn't my focal point, it doesn't matter for this limit problem. But if we were to do the same problem and my limit was as x approaches negative 2, then we would be having an issue because you can't cancel out the problem there. And then we'd have to resort to like graphing or the table. Okay, so that's the new strategy that we just used. We need to flip the page. And we're going to list some strategies here. So one strategy is you can factor and divide or cancel like factors. Then try direct substitution again. So that's one strategy that you can use there in that problem. I'm just checking my time here. We're at 20 minutes, so I'm going to call it good for your notes this weekend. When you come on Monday, we will probably do the last 3 together. Whoops, I totally skipped one. No, I didn't. Yeah, the last 4 problems together and finish out these strategies. So keep that in mind when you come on Monday. Have a good weekend.